So we're going to take a look at gravity in orbits, and the context is this homework question dealing with an orbit. And when you're talking about orbit, you're talking about several concepts all put together. You're talking about circular motion, where A is equal to V squared over R. And you're also talking about V equals 2 pi R over capital T. So in this one, we're given the R and the capital T of an orbit. So the first thing we can do is we can figure out the speed of this thing. So let's say Phobos is this gray rock. It's following a roughly circular orbit around Mars, and we'll have it go this way. So we can definitely go V equals, we can just plug numbers into a formula. There's the R, there's the T, we plug them into the formula, we get a number for V. So so that part's easy. Then, since this is circular motion, we know the acceleration is the same thing. And then we have to think about the force diagram for this thing. This object is experiencing just the force of Newtonian gravity. I'll use a capital G for it instead of the lowercase g. So our force of gravity is equal to G m over R squared. So when we look at our force diagram, we basically have the force of gravity is equal to mass times acceleration. And that means that G capital M lowercase m over R squared is equal to mass times V squared over R. Because we can plug in this A for the A using the number we get from V. And to tell you the truth, we'll have the A as a number, so we might as well just put it in as just itself instead of as a formula. Why make the formula more complicated if we have a number? And then the lowercase m's cancel. And out of these things, what do we know? What are we looking for? We know that G is 6.67 times 10 to the minus 11th. And we know R is a number, and we know A is a number. It is M that we're looking for. So then we solve for M, and we just multiply both sides by R squared and divide both sides by capital G, and that is mass of the planet. And most gravity situations, Newtonian gravity situations that you have to analyze, will end up using these formulas. These are for circular motion. This is gravity, and occasionally we'll need the potential energy due to capital gravity is minus G m big M little m over R. And yes, with gravity in orbits, we tend to flip-flop back and forth between capital and lowercase r. They don't mean anything different. They're the same thing. So make sure that you know how to identify situations in which circular motion is important, and then that you can pick out the formulas from the equation sheet that deal with circular motion, and then look at the given information here. We were given the orbital radius, so that fits directly into all these formulas as r. We were given the period, that's this capital T. And this formula here is on the equation sheet. It's basically a speed is distance over time formula, saying that the distance for one orbit and the time for one orbit correspond to each other. So that is the distance and time for the same process. The process is one loop around the orbit, and that's how we calculate the v to get circular motion. Then we need to figure out how that fits in with the Newtonian gravity force. A little force diagram that we make sure that, okay, that force is mass times acceleration. It's the only force. So we set it equal to object mass times acceleration, and then we find that we can solve for the missing piece.